Hi, this video we're going to look at some derivative rules for logarithmic and exponential functions. So there's a chart here that shows some derivative rules. So for the function ln of x, the derivative is f prime of x is 1 over x, right? So okay, that's a memorize thing. And then we've got a derivative for the second function in the chart here is log base a of x, where a would be whatever constant we might have, maybe a base 10 logarithm or whatever logarithm we might have a need for a base of. That a would just be a constant with a few restrictions on that. So that derivative is pretty similar to the previous one. You have this extra factor of ln of a in there. And then f of x equals a to the x, where we've got this exponential function here. One important thing to remember about this kind of function is that I've got x in the exponent here, not in the base of the function. So with that x up in the exponent, that's an exponential function. That's not the same rule that we would use if we were finding the derivative of something like y equals x squared, where the variable is in the base. So this would be the rule that we would use when we want to find a derivative of something like y equals 2 to the x, constant base to variable power. All right, and so that derivative is a to the x ln of a. The y prime would be 2 to the x times ln of 2. As an example of that last rule. We also had one other rule for exponential functions from before, so we've been working with this one for a while. I'm just going to add it on top of the table here, but we know that if we have a function f of x equals e to the x, its derivative f prime of x is also e to the x. Kind of an unusual function that is its own derivative. That's not very common. Alright, so that's also an exponential function, and that would work if we apply this rule down here at the bottom of the table with e to the x, because ln of e is just 1. So if I try to apply that rule at the bottom of the chart here to my function y equals e to the x, and I try to do it this way, I'd get y prime equals e to the x ln of e, but since ln of e is just 1, I can simplify that to be just e to the x. So that's consistent with the rule we already knew. Okay, so we're just going to look at a couple of examples of these. As you do the examples, that should help you memorize these, but you may also need to spend some time with flashcards or whatever other method that you might use to help yourself memorize things. But you need to know all of those. You probably already have this one memorized up here at the top, but these 3 new rules. Okay, so we're just going to look at some examples using that, and some of these examples involve product rule or quotient rule or chain rule as well. Okay, so the first example down here, we've got y equals 3 ln of x, and anytime you're taking a derivative of anything, one of the things you want to pay attention to is where are the variables. So the first thing I would notice is that I only have one variable in the input of the function here, one place that there's an x in the input of the function. So I don't need any product rule or quotient rule or anything like that. I just have a constant out front times a basic function that I have just learned a derivative rule for. Alright, so this is my original function, y equals 3 ln x, and then my derivative, y prime, equals, the constant out front is going to just come along. That's a rule we had from earlier. Derivative of constant times a function is just going to be that constant times the derivative, and then times the derivative of ln of x. So that's one of the new ones in the chart here. So derivative of ln of x is 1 over x. Alright, so then I can simplify my answer and I just get 3 over x. Okay, one word of caution before we go on to another example. Every once in a while I see some student write silly things, like they'll write something like y equals ln of x equals 1 over x. That's not true. That's false. Ln of x is not the same as 1 over x. One of them is the function and one of them is the derivative. They are not the same thing. So don't write that the derivative is equal to the original function. That hopefully is a habit that if you ever started that, you've already stopped it. But that's something you need to stop if you're doing anything like that. So just check your work, check your notation, make sure you've got the original function labeled y or f of x or whatever it's called, and then your derivative labeled using some correct notation for a derivative and not an equal sign in between them. Okay, so let's go on and look at a couple more complicated examples here. So this next example, we've got y equals x times ln of x to the fourth plus x. So pay attention to where the variables are. I'm going to notice there and there and there. Okay, so the first thing I might notice is that I have this x times an ln function. So there's going to be some product rule going on here. The second thing that I would notice is that unlike the previous problem where I just had ln of x, on this one I have ln of a bunch of other stuff that's not just x. So on the second factor in my product here, I've got an outer function, which is an ln function, and then an inner function, which is x to the fourth plus x. Alright, so you should be saying to yourself what the rules are that you're going to need to use here and thinking about setting that up. You might pause the video and set up your paper and then restart the video to see if what you did is right. Okay, so let's just go ahead and fill in the stuff here. So derivative of the first function, derivative of x is just 1. And then the second function, I'm just going to write down that second function, plus the first function, that's just x. And then here, when I go to take the derivative of the second function, that's where I'm going to need chain rule and probably bigger parentheses. So I'm going to erase the back end of that. Okay, so derivative of the second here, this is where I'm going to use chain rule. So the derivative of the outermost function, derivative of natural log of something, is 1 over that something. In the previous problem we had up above, we just had ln of x as the original function, and then the derivative was 1 over x. So here we've got ln of a bunch of stuff. So the derivative of the ln part is just going to be 1 over the bunch of stuff that's inside. Derivative of the outside part, leave the inside alone. So that's the derivative of the ln part, the outer function. And then I need to take that times the derivative of what's inside. So I'm going to look at that x to the fourth plus x back in my original function here as the that I've labeled as an inner function. I'm going to take that whole thing times the derivative of x to the fourth plus x. So 4x cubed plus 1. Okay, and so we've got a lot of unnecessary parentheses in here that I don't actually need, but there are a couple of necessary parentheses here that would be wrong if I left them off. So I'm going to highlight those. The stuff inside the logarithm function needs to be grouped so that it's clear that the logarithm applies to all that stuff. If I leave off those parentheses around the stuff inside the logarithm function, then the ln would only apply to whatever is the very first term there, just the x to the fourth term. The other place where the parentheses are really necessary here is that I have a bunch of stuff here at the end times the 4x cubed plus 1. And if I was going to distribute that through, I would need to distribute that through to 2 terms. If I leave off those last set of parentheses, then all that stuff I have out front would really only be times the 4x cubed part and not the plus 1 part. Okay, so I could leave what I have exactly like that, or I could tidy things up a bit. I'll go ahead and do that, and then we'll look at a couple more examples. Okay, so let's just finish tidying this up. I'll have y prime equals 1 times that ln function. I just can write ln of x to the fourth plus x. All right, and then everything I have after the plus sign, there's a couple ways I can handle that. One of the things that I have in there is a fraction. So I might rewrite both of these other two things as fractions and then think about just multiplying straight across. All right, so then I would have x times 4x cubed plus 1 on the numerator, and then on the denominator just x to the fourth plus x. Okay, so I could leave my answer like that. The only other simplifying I could do is I might notice that on this last fraction I have a common factor of x on the denominator, and so this x to the fourth plus x, I could factor an x out of that. So I'm just going to factor it and write that right below there. I didn't cancel anything, I just replaced that denominator with it in its factored form. But the goal of doing that is that I can do some canceling, the x factor that I have on the numerator and the x that I factored out on the denominator then would cancel. And so I'm left with ln of x to the fourth plus x plus this last fraction, 4x cubed plus 1 all over x cubed plus 1. All right, it's tempting in that last fraction to start crossing other things out, but I don't have any common factors in that last fraction, so there's nothing else that I can cancel in that last fraction. So there we go. All right, let's look at another example here. Okay, so 5 times 2 to the x. Okay, so we had 3 new rules this time. I'm going to scroll back up to that chart so we can look at that rule and kind of think about what's going on here. All right, so the rule that we're going to be using for this one, and in fact I actually did an example kind of down below the chart that was relevant. So if I have y equals 2 to the x, then I'm applying that last rule in the chart to find that derivative. Okay, so that last rule in the chart is the one we're going to use on the 5 times 2 to the x example that we're looking at down below. So we want to make sure we write that rule down or remember it. You need to memorize it, so practice writing it down. That'll help you remember it. All right, and then let's go up here and we'll do this problem here. All right, so we have 5 times 2 to the x. So pay attention to where the variables are. Variable in the exponent, so that's an exponential function. That's that new rule we have. This is not a bring down the exponent and subtract 1 rule. When you have variable in the exponent, that's a different rule. That's the rule we're working on now. All right, and then the other thing I would notice is that that's the only place I have an x. I just have a 5 out front. So when I find the derivative, my y prime is going to be equal to my 5 that's out front is going to just come along. Derivative of a constant times the function is just that constant times the derivative of the function. And then I'm going to apply that new rule for differentiating 2 to the x. So just like we did up above, derivative of 2 to the x is 2 to the x times ln of 2. And I could put some parentheses around that if I want. That stuff in the parentheses came from the derivative of 2 to the x. All right, so I could probably leave it like that. Maybe put some parentheses there. I could write it as 5 times 2 to the x ln of 2. It would be okay to leave your answer like that. If you are really ambitious or really love logarithms and properties of logarithms, you could use a property of logarithms to rewrite this. I'm going to use commutative property and switch the order on the factors here. So I'll rewrite this as 5 times ln of 2 times 2 to the x. And then I'm going to use a property of logarithms on this first part here, which you may or may not remember. But that property, I'm going to write it off here to the side in red here, says if I have ln of a to the b power, ln of a to the b power, that is b times ln of a. That's not a derivative rule, that's an algebra rule, property of logarithms. Okay, so I could use that property on my 5 ln 2 if I really want to. So my b would be 5 and my a would be 2 here. And so I could rewrite that as ln of 2 to the 5th, which is 32. All right, so if I want, I could write it like that, or 2 to the x ln of 32. Okay, so any of those things that I have for the y prime equals, any of those things would be okay answers. You could just leave it like we had at the beginning, or do however many steps of simplifying you decide is appropriate to do. All right, we got one more example to look at here, so let's scroll up a little bit so you've got some space to work on this one. All right, so there's kind of a lot going on in this problem, and it's also the last rule that we haven't done an example of yet that's in this chart at the beginning of the video. All right, so pay attention to where the variables are, there and there. So I have one in the numerator and one in the denominator. I have a quotient of 2 functions involving x, so the overall structure of the problem is going to be quotient rule. So I'm going to set up some parentheses for that. Okay, so there we go. So the places where I'm going to need to take the derivative of the top and the derivative of the bottom, I need to think through if there are any other additional rules I'm going to need to use on that. The derivative of the top, it's really just a polynomial. 2x squared minus 1, that's easy to take the derivative of, so that one's not complicated. The derivative of the bottom, I have a rule for a logarithm. Let's scroll back up to that chart and look at that. So that would be a rule for log base a. The a would be 3 here. So our derivative would be 1 over x ln of 3. right? So derivative of log base a of x is 1 over x times ln of a. All right, so we're going to use that rule here, and our a would be 3 on that. But the other thing that you might notice here is that I don't just have log base 3 of x, I have log base 3 of some stuff that's not just x. So actually there's some chain rule going on there. When I find the derivative of the bottom, there's going to be chain rule, and my outer function is the log base 3 function, and then the inner function is 2x. Okay, so let's just fill everything in here. So the derivative of the top, derivative of 2x squared minus 1, that's pretty easy. Bring down the exponent, subtract 1, so I get 4x, and then the derivative of the constant term all by itself will just be 0. So I don't really need to write the 0, but I'll just put it there. And then times the bottom minus the top. That's just copying that down. And then here times the derivative of the bottom. So remember, derivative of log base a of x is 1 over x times ln of a, the ln of a on the denominator. So here we'll have 1 over, not just x, but 1 over 2x times ln of 3. Right, so that's the derivative of the log base 3 part of the denominator, and then times the derivative of the inner function. I'm going back to my original function and looking at what is the inner part on that logarithm function to figure out what I'm taking the derivative of here. So the derivative of the inner here is just the derivative of 2x, which is 2. And then the bottom squared, so log base 3 of 2x and the whole thing squared. Okay, so there's some parentheses I have here in red. I'm going to go back in and put in the ones that are really necessary, so that would be incorrect if you didn't have them there, and then we'll write a tidied up answer. All right, so on the first term here, or first factor, I wrote 4x minus 0. That 0, of course, is not really necessary, so let's just get rid of that. It's just 4x times log base 3 of 2x. Really, the only parentheses I need there are around the 2x that I already have in there. And then I have minus, and then after the minus, one of the things you should notice is that you've got two terms here. I need parentheses there because otherwise the minus sign out front would only apply to the 2x squared and not all of that. And then all of that stuff is going to be times these factors I have here at the end, the 1 over 2x ln 3 and 2. I don't actually need any other parentheses on the top except the 2 that I have here. On the denominator, really the parentheses I have in blue here are the ones I need enclosing what's inside the log base 3 of 2x, and then these other parentheses here on the outside. One thing about the way the original problem was written, they didn't have parentheses around this stuff that was inside the log base 3 of 2x, and so sometimes you'll see it written like that, but really better notation to include those parentheses there. It wouldn't actually be incorrect to leave off the parentheses around the 2x's that I have here in my answer, but probably better to leave it there. All right, so let's tidy this up. Y prime equals, before the minus sign on the numerator, I'll have 4x times log base 3 of 2x. And then after the minus sign, I'll have minus 2x squared minus 1, that whole quantity, times. And then this last part here, I've got a couple fractions times each other. So I might write the last 2 over 1 and then just multiply straight across. So I'll have times 2 over 2x ln 3. Those 2's there can cancel. We'll do that next. On the denominator, log base 3 of 2x, the whole thing squared. Okay, so these 2's in this fraction here at the end can cancel. I have something like that. All right, so I could leave my answer like that. I would want to make sure I leave a 1 on the numerator here. It's maybe not the best form to leave an answer like that where you have a fraction within a fraction. We did some simplifying of things like that when we did limits, actually, where we were doing the limit definition of the derivative and we had fractions within fractions. We had to do some simplifying of things like that. So one way you can deal with that simplifying is when you have these fractions within a fraction, if you multiply through the entire numerator by the common denominator of those little mini fractions that are within the larger fraction. So in this case, that would just be the x ln 3. And if I multiply the numerator of a fraction by something, I should be multiplying the denominator by the same thing. so that I'm really just multiplying by a form of 1. Same thing, numerator and denominator. Okay, so let's go ahead and simplify that and clean that up. All right, so y prime equals, I'm going to take my x ln 3 that I decided to multiply through by and multiply that to that entire first term, everything before the minus sign. So I'll have 4x squared ln 3 times log base 3 of 2x, a whole bunch of stuff in that first term. And then when I distribute that to the second term, the whole point of doing that was that the x ln 3 that's on the denominator would cancel with the x ln 3 that I'm multiplying by, and I would get rid of that fraction. So I'm just going to be left there with the quantity 2x squared minus 1. And actually, I might go ahead and distribute that minus sign through on this as well, on these last two terms. Okay, so there is the numerator, pretty much as simplified as I can get it. On the denominator, I have the original log base 3 of 2x, the quantity squared that was already there, and then that's going to be times the x ln 3. I think I'll write the x ln 3 out front. And I can write log base 3 of 2x, the quantity squared, or this may be a notation you haven't seen much before, but I could write log base 3 of 2x squared, similar to how you might write something like cosine of x, the quantity squared, as cosine squared of x. So similar to how you might do that with trig functions, you can also do that with logarithms. Okay, so there is an answer. It's kind of a mess, but there is our answer in simplified form. Actually, if I go back up to what I had before I removed all the extra parentheses, that is correct also. It's just unsimplified. So what I had in red up here at the top, including the blue parentheses, but I don't necessarily need the red ones, that was all correct as well.